right, hi, welcome everyone. Thank you for coming. Hope everyone's been having a great time at Remars. My name is Angela Sun. I lead product on the Alexa speech recognition team, and I'm here with my colleague Erin today, and we'll be talking about self-learning on Amazon Alexa. So I'm gonna start off with a quick overview of Alexa speech recognition, and then I'll talk about why a self-learning system makes sense for us. And then I'll turn it over to Erin. He'll go over an introduction of self-learning, a system overview, and we'd love to answer any questions you have at the end for us. So Alexa speech recognition. Our vision is to enable Alexa to recognize speech for anyone, anywhere, with superhuman accuracy and speed for any type of interaction in the cloud and on the edge. So I want to give a bit of insight into what that means for a voice assistant like Alexa. So Alexa recognizes speech anywhere. If you think about humans, speech recognition is the clearest when a person is facing you and talking quietly in a room. This is the same for Alexa. So we think about the device location. Where is the device in your home? What room is it in? And what acoustic environment is around that device? We think about proximity to the device. How far or how close is the speaker speaking to the device? And we also think about background noise, which can be quite dynamic in the house. If you're like me, I have my Echo in my kitchen, and I am asking for recipe information. I'm asking to set a timer all the while my sink is running and my kids are playing. And so if you think about it, Alexa has to recognize speech over all of that background noise in any type of environment. And then let's expand that to all of the different form factors that Alexa operates in. So Alexa has to recognize speech for any one of hundreds of movies that were released in North America just last year, thousands of TV shows in Japan. And we also notice unique user patterns on when users use Alexa on the television. They perform what we call content-only searches. And so they tap the remote and they can say Encanto versus explicitly stating what their intent is, which is play the movie Encanto. And we also operate in a number of on-the-go environments. Alexa is in the car, we're on hearables, wearables, and as you saw in the booth and some of the talks, we've also announced that Alexa will be part of the NASA's Artemis mission to space. And all of these present really unique speech recognition environments. Now let's think about recognizing speech for anyone. At Amazon, we work backwards from the customer. So as we think about individuals, we have to recognize and deliver great experiences for customers, regardless of languages, regardless of whether or not they speak multiple languages or multiple languages are spoken within the household, dialects, accents. Recently, we announced that we launched enhanced speech recognition for people who stutter. And so really we're looking at the breadth of speech patterns and making sure that Alexa can have that great experience regardless of the type of speech. We also really want to adapt to the way customers naturally speak to Alexa. So an example here is a child wants to ask Alexa for unicorn pajamas. And at home, she can refer to pajamas as jammas, pajamas, and Alexa really, we want her to feel familiar. And so Alexa needs to be recognizing any number of ways that a person wants to say a particular word or a phrase. So I'm gonna talk a little bit about why we should build a self-learning system. First, what is self-learning? Simply put, traditional machine learning has required humans to label data. And so what that means is that a person is transcribing clips of audio in relation to speech recognition. And that requires not just time and people, but also a lot of times it requires cultural and language expertise, right? You have to know that the Las Vegas Raiders is a football team in the US, and any type of requests that people make to Alexa. Self-learning does not require human labeled data, and so it's a system that's really relying on system-generated labels. What this means is that we can move much faster in a cost-effective way and more privately. So why is this important to us? As I already mentioned, scalability is key for us as the Alexa's applications grow, the device form factors grow, but at the same time, the volume of information and content in the world is also growing. So let's look at a couple of examples. The hours of video uploaded to YouTube every minute is 500. What that means is in the hour that we're here today, 30,000 hours of new content, new videos are uploaded to YouTube. I use Alexa a lot for Spotify music, and so can anyone guess the amount of tracks uploaded to Spotify every day? It's 60,000, and that's in one day. And so again, our system really needs to keep up with the speed of information as well to facilitate our customer needs. Speed is also very important. As I mentioned, self-learning enables us to move much faster without humans in the loop. And so speed is specifically important because of trending topics. And so at Alexa, we really look at trending topics in two ways. We have seen trends, which we can anticipate, like the Olympics and events that are scheduled. And then we have what we call unseen trends that we can't really anticipate. And those are typically late-breaking news, such as Omicron, Brexit, TikTok trends. And so our system really needs to be able to keep up with what we see in terms of customer usage. Privacy is also very important at Alexa, and so a self-learning system without human-labeled data allows us to limit the need for human transcriptions and also, as well as, limit the need for data storage. Lastly, it is also a system that will help us with personalization. As I mentioned earlier, it's really important that we meet the individuals with how they speak and the specific accents and usage patterns, vocabulary, and whatnot. And now I'll turn it over to my colleague Aaron, who will go much deeper into the how.
Thanks, Angela. So first, I'm going to give you a high-level overview of self-learning with a little bit of details of the types of things that we do in our system, and then I'll get into the system itself. So first off, what is self-learning? Angela kind of described it, but in machine learning, there are two broad approaches, unsupervised learning and supervised learning. So in unsupervised learning, when you're training the model, you don't have to give it a label. You don't have to tell it what the correct answer is, and it can just learn from the structure of data itself. For example, a clustering algorithm may group things together that are similar. But the much more common approach, and the approach that we use, is supervised learning. So that's learning with the labels. So we have to have, and typically we have humans produce these labels. So we'll take all the training data, and humans will review it to add the labels. And then we can use that when we're training the model to see how close the model came to the correct answer, and then use that information to improve them. Self-learning is essentially doing this supervised learning without human labeling. And instead, the system itself labels the data in some way. In our system, we use three different types of self-learning. We use semi-supervised learning, weakly supervised learning, and self-supervised learning. So the first one is semi-supervised learning. And this is the one that we use the most. And it's called semi-supervised because we still use a small amount of human-labeled data, but we combine that with a much, much larger set of machine-labeled data to train our models. So I'll walk you through how that works. So here we start with this small amount of human-labeled data. And what we're going to do with that is we're going to use that to train what we call a teacher model. So a teacher model is a more accurate model that makes better predictions than our production model. You might wonder if it's better, why wouldn't we just make this our production model? And the answer is latency. So these teacher models are typically much larger than a production model. They can hold more information and make better predictions, but they're just too slow to handle real-time customer requests. Another difference is that in ASR, we have to process the audio on the fly as it's streaming in. So as bits of audio are coming in, we have to be making predictions on the fly. We can't wait for the entire stream of audio to then make the prediction because it would just be too slow. But the teacher model doesn't have that restriction. So we can give it the entire stream of audio, and it can use all the context from that audio to make the best prediction. We could even take it a step further and expose it to the entire back and forth dialogue between a customer and Alexa to give it as much context as possible. And that will allow us to produce the best label possible. All right, so now we have this bigger, better teacher model, and we can then use that to go label a bunch of unlabeled data. And this unlabeled data is usually many orders of magnitude larger than the human labeled data. And that produces what we call pseudo-labels. We refer to these as pseudo-labels to differentiate them from the human labeled data. And so once we have this big set of pseudo-labeled data, we can take that and a smaller amount of human labeled data to train our student. And our student is our production model. So we're effectively distilling knowledge from the teacher to the student via these pseudo-labels. And this works really well, but there are a couple of downsides to it. One is that the teacher is a model, and so it can also make mistakes. And so when the teacher makes a mistake, it shows up in the pseudo-labeled data as an error, which then can translate into the student starting to make mistakes. This phenomenon is called self-reinforcing errors. So we have to figure out how to break that cycle of errors. The other downside is that if the goal of this self-learning approach is to do it without human labels, yet this approach still relies on a small amount of human labeled data, how can we shrink that reliance down or break it completely? And the next two techniques that I'm going to describe will help in those areas. So the next area is weakly supervised learning, or weak supervision. So in weak supervision, you take multiple high-level signals that may be somewhat noisy, and you combine them together to produce a pseudo-label. So these signals could be feedback signals from your systems that are telling you that you got something wrong, or it could be feedback signals from customers that tell us that we did something wrong. So I'll walk you through an example. So in this case, some audio is streamed into ASR, and we produce the prediction, the text output that we think the customer said. We then pass that text down to the next component in the Alexa pipeline, natural language understanding, or NLU. NLU's job is to take that text and figure out what the customer's intent was, what action do they want us to take. And that already provides some useful feedback. So if NLU couldn't find a useful action to take, that might mean that ASR got it wrong. It also might mean that the customer asked for something that we just don't support. And so that's why it's a bit noisy. We don't know exactly what was the case. So you have to sometimes add on additional signals to help make sure that we're understanding that feedback signal correctly. Finally, once we've processed the request, we're going to take some sort of action on behalf of the customer. And in the case we get something wrong, like let's say we play a song, but it's the wrong song, the customer may either give us explicit or implicit feedback. They could explicitly say, Alexa, you did this wrong, which is a very strong signal. Or they could barge in and stop the playback and say it again, hoping it will get it right the second time, or rephrase what they said a little bit. And these experiences of friction that the customers have and the feedback they give us either implicitly or explicitly are very helpful for showing us that we did something wrong in the system, and in some cases, telling us what the right answer is. So here's a kind of a trivial example that just illustrates this. So the customer asked for what's the weather in Austin? And we misheard the customer and said the weather in Boston is, and then the customer interrupted and said, no, Alexa, what's the weather in Austin, Texas? So now we have the additional context of Texas, so we know that they meant Austin. And we can use that to learn that audio that we heard wasn't actually Boston, it was Austin, and correct that error in the future. So the last type of self-learning that I want to describe is self-supervised learning. This one's a little bit different in that you don't rely on some external entity to provide you with a label. So there's no teacher model or weak supervision happening. In some cases, the model you're training itself provides the label. And that seems kind of counterintuitive because if you're trying to improve a model, but you're relying on that model to tell you what the right answer is, how does it ever get better? One technique that we use is called noisy student training. So in the ASR world, what we do is we take the original customer audio and we feed it into the model we're training, and that will produce a prediction, and we're going to treat that as our label. We can then augment the original audio with background speech, noise, reverberation to make it a more challenging learning case. We can then feed that augmented audio and the label from the clean audio into the training model to improve it. And what this does is it helps make the model more robust to those challenging acoustic conditions. Another type of self-supervised learning that we do is representation learning. So in representation learning, you don't start out by training an ASR model directly. Instead, you train a model that understands the structure of Alexa-directed speech, the representation of that. So it can predict what Alexa-directed speech looks like. And we can do that in a variety of ways, but the example I have here, we're giving the model several seconds of audio, and then it has to predict what the next couple of seconds of audio are. So in this one, we gave it Alexa Play Muse, and it predicted that it should have been Alexa Play Music. So once we train this model to understand the structure of speech, we can then change the objective function of the model to perform ASR tasks. And then we can fine-tune that on ASR examples to train an ASR model. And what we found is that by doing this pre-training of the model to understand the structure of speech, we end up with a better overall ASR model with much less labels. So that helps kind of reduce that dependency on human labels. And these approaches are complementary. They're not mutually exclusive. For example, we might start with a brand new model and use representation learning to pre-train it to understand the structure of speech. We could then fine-tune it using semi-supervised learning with our teacher labeling for us. And we can use weak supervision to correct any of those errors that the teacher may have introduced. And then finally, once we have a good model, we can use noisy student training to make it more robust to these challenging acoustic conditions. So another concept that I want to describe here is incremental learning. So in traditional machine learning, you train a model from scratch. So you take a model that has never seen any data, and you take all your training data, and you train it start to finish. And the reason why people do this is because you can have really fine-grained control over exactly what data goes into your model, which is important. You can also randomly shuffle the data so that it's well distributed, it doesn't have any biases. But an alternative is incremental learning. So in incremental learning, you don't start from scratch. You take your existing model and you simply apply the new data that's come in since the last time you trained. So every hour, every day, every week, you would just take all the new data that came in and apply it to the existing model. This is a lot faster way to train, and so it allows us to more quickly keep up with shifting usage patterns and trending topics. And it also is cheaper because we don't have to process nearly as much data. So you might think that, yeah, this totally makes sense. Why doesn't everyone just do that? And the reason why it's not super common yet is that it has a couple of challenges. One is that you might bias the model. So if you have a small window of time of new data that you're applying on top of your model, that data may be heavily biased. For example, if you take like an hour in the morning, maybe it's just people turning off their alarm clocks, and in the evening it's just people setting their alarm clocks. And so if it's just about that, the update will be biased, and you might bias the model so that it prefers those types of use cases at the expense of others. Another downside or challenge we have to overcome is catastrophic forgetting. So these models have a limited capacity for holding information. They can't remember all things for all time. And what we see is as we apply the new data on top in an incremental way, the model tends to forget things that it hasn't seen in a while, older data. And I'll describe in a little bit how we address these challenges in our system. All right, so now I'm going to walk you through the system itself. So in traditional machine learning, all the data from customers' edge devices gets streamed into the cloud. And then the data that we select for training gets stored into a centralized repository for a period of time. And then the actual training processes happen offline, either on a scheduled basis or an ad hoc basis. So first we have to label all that data in the centralized repository, either by humans or by machines. And then in a separate cadence, we do the model training. Maybe every week or 2 weeks we're training these models. But we're holding that data, this large amount of data in the centralized repository to do that. If you compare that to the system that we're describing here, you can see that in this case, the audio still comes into the cloud, but it gets intercepted by this real-time learning service. The real-time learning service will automatically label the data using the self-learning techniques that I described. And it will do a portion of the model training. So it computes what we call the model update. The model update is essentially how we should change the model to improve it. Once it has the model update, it no longer needs the audio, so we can discard it. So we don't have that centralized repository of audio anymore. And then the learning service can send these model updates to this learning orchestrator to combine them all together to produce the final model. This is novel because this whole thing is running in a streaming fashion, so it's doing real-time labeling with self-learning techniques and reducing the time we have to hold onto audio to as small as possible. And this approach is inspired by federated learning in a bit. So federated learning is an approach to machine learning where you actually do the training on customers' edge devices, or a portion of the training. So you, on your Echo device or your phone. So on the device, we'll actually automatically label the data and compute these model updates, just like we did in our real-time learning service. And then the model updates can be sent to the cloud, and the data never has to leave your device. So it's a much more privacy-preserving ML approach, and it's the direction we're heading. So now I'm going to walk you through our self-learning process. It's not all that different from a standard ML training pipeline, except for that it's happening in real-time streaming fashion. So we start with some real-time data. The first thing we have to do is select the data that we want to use for learning. We get huge volumes of data, more than we can possibly train with, and some of it's not useful either. So we want to filter down to the really useful data. Once we've selected that data, we then extract our audio features using just our standard audio feature extraction processes. And then we generate the labels using those semi-supervised or self-learning techniques that I described before. So now that we have the features and the labels, we can feed them into the model to compute the model update. And I'll go into a little bit more detail of how that works in a bit. But essentially what it does is it produces a gradient. So the gradient is the delta we should apply on top of the model to improve it. And then we can finally take that gradient and apply it on top of the model to update it. And then we just repeat this loop over and over and over again, continuously, to keep improving the model. This loop, one pass through this loop is what we call a round. Sometimes it's called a step, but we typically refer to it as a round. And currently, this round takes about 30 minutes. The part from real-time data to gradients takes a few seconds. That part's really fast. That's the near real-time part. But the application of the gradients to the final model is the long pole. And the reason for that is a couple of things. The real-time service that's computing these gradients is running on hundreds of nodes to scale up to the traffic volumes that we have. So each one of them is producing one of these gradients. And so when we update the model, we have to combine all those together to create a single gradient. And we're also using batching. So we don't want to update the model on every single request. So we wouldn't just take one request, produce one gradient, update the model. It's just inefficient. So what we do is in that gradient step there, we actually accumulate the gradients, accumulate several hundred gradients on each of these nodes. And so that also adds time. This is our high-level view of our system. And I'm going to focus on 3 components here. The learning service, that's that real-time learning service that's computing the model updates. And you can see on the left, we have real-time streams feeding into the service, whether it be customer requests or those weak feedback signals that we use for weak supervision. The audio gets stored in a short-lived audio buffer, in-memory buffer, for a matter of minutes. And that's where we pull the audio from if we decide we want to learn from it. And this audio buffer already existed for some production use cases. And so our goal was to reuse it and not have to increase the retention time at all. So the learning service produces these model updates and then passes them, remember, across hundreds of hosts. And then it passes all these into the learning orchestrator, which will produce the final updated model. The other component that I wanted to describe is the offline trainer. So the offline trainer is actually real similar to the learning service. It's doing the exact same operations. It's taking data in and producing model updates that can then get combined with the model updates coming from the learning service. The difference is instead of operating on real-time data, we have a small store of historical data, older data that we keep around. This could be historical human-labeled data, or it could be synthetic data that we generated to look like real customer data. And so the offline trainer is responsible for creating model updates on this older data. And I'll get into why that's important in a little bit. So first off, let's talk about the learning service. So it's a real-time service hosted on Amazon Elastic Container Service, or ECS. We chose ECS because it allowed us to really easily containerize our logic in a Docker and then spin up fleets to handle new use cases and models. It also allows us to easily scale up and scale down our fleets as traffic volumes change throughout the day. It's responsible for selecting and labeling the useful data that we want to use for learning and for computing those model updates. So we have a few different learning sources that we use. The first and foremost is the real-time customer data, of course. We want to make sure that we're learning the ways that real customers are using Alexa so that we keep up with that as trends shift over time. We also want to learn about trending data. So if there's some new hot topic in the news or a new song name or a new artist, we want to make sure that we learn those things really quickly. So we have external systems that I don't cover here, whose job it is to go out and find all these trends and figure out what's the list of things that we should make sure we focus on. And so that data can be fed into our system so we can focus the training. And then the final source is these feedback signals, these errors that we're getting that we can then correct. All right, so we have all these different data sources. So how do we select the data that we want to use for learning? The first approach we did was something really simple, just random sampling. So we have this huge volume of data. Let's just select 5% randomly. And that worked pretty well. We got some decent results. but we did see a couple of things. First, we tended to select some things that were just super easy, like Alexa stop, Alexa play music, things that ASR was already really good at. And so it didn't really add value to learn from those. On the flip side, we saw examples that are just essentially garbage, like just they're so noisy that even a human couldn't tell what was being said. And those can actually hurt our models if we train from them. So we next introduced confidence-based filtering. So the ASR model, in addition to producing the text output, also produces a confidence score, and that's the likelihood that we got the prediction correct. So if we get a really high confidence score, there's a good chance that the text is correct. If the confidence score is very low, there's a pretty good chance that there are errors. And so we pick a confidence band somewhere in the middle to filter out those really easy ones and to filter out those impossible ones. And it leaves us with a nice set of challenging examples. And the confidence-based approach, combined with random sampling, does a pretty good job of giving us overall improvements across the board. But we wanted to also focus on specific use cases. So we also added cohort-based sampling. So in cohort-based sampling, we are able to focus our training on a specific group of customers. For example, we might want to prefer to train on requests coming from a new device that we just launched. We want to get more data to train on from that device to improve the experience there. Or we might focus on a particular use case or domain, people asking about politics or asking to play music. And so we can kind of target down to the specific use cases to make sure we improve things there. And then finally, we can also focus on people in a particular geographic region or people with certain speaking characteristics that are maybe not getting as good a performance. So we can raise their accuracy up and make sure that ASR works well for everyone. And then the final selection criteria is those errors I mentioned. So if we do know about errors, we definitely want to prefer those because those are things we got wrong that we want to make sure we don't get wrong again. All right, so now that we've selected our data, we have to label it. So for this, we just use the 3 different types of self-learning techniques that I described. So we use semi-supervised learning primarily. So we do have these bigger, better teacher models, and we actually have multiple of them. And so in some cases, we can run all of them in what we call an ensemble of teachers, and then we can combine the outputs of all those teacher labels to provide a better overall label. And we use these feedback signals to do weak supervision, and that can correct our model that we're training, but it can also correct our teacher model so that the teacher doesn't propagate errors to the student. And then finally, we can go without labels and use self-supervision through noisy student training or representation learning to do training that way. Okay, so now that we have the labels and we have the features, again, the feature extraction is pretty standard, so I'm not going to cover it. We have to do the model update calculation. So we just use a standard gradient descent algorithm. So we feed the features into the model, and it makes some prediction of what we think the text was. We can then compare that output, that prediction, to the label to see how close we came. And we do that by feeding the label and the prediction into what we call a loss function that will tell us basically, I think my mic, how big of an error we made. And then we can use that information to do what we call backpropagation. So we'll go backward through the model, calculating how we should update the parameters at each layer to reduce that error and improve our prediction. And that results in these gradients that I mentioned before, the deltas that we want to apply to the model to improve it. And as I mentioned, we don't update the model one by one, so we accumulate these gradients on each server node for several hundred requests. And the accumulation is essentially, there's different ways you can do it, but currently we use just a running average. So as a new gradient is produced, it just gets averaged in with this overall running average. And what that does is it ends up giving us kind of a nice average gradient that can help improve in a lot of areas and not just for one specific use case. But these aggregated gradients, again, are being produced on hundreds of different hosts, and they each have different ones. So we have to combine them together somehow. And that will be taken care of in the next system that I'm going to describe, the orchestrator. So you can think of the orchestrator as sort of the brains of the system. It's the stateful thing that tracks the process as we're going through these rounds of training and checkpoints the model along the way. So if you want to start a new training, you interact with the orchestrator and say, I want to train this model with this algorithm and these parameters. And then it will start that process and communicate with the servers that are fairly stateless to tell them what to do. The learning orchestrator also is responsible for that global model update, to take all those gradients coming in from all the hosts and turning it into a new model. And then finally, once it's updated the model, it will have to do an evaluation of the model to see to make sure that the model is improving the way that we expect. So talking about the global model update, the first thing we do is we, once again, average all the gradients together. And we do a weighted average, because some of the gradients may have more requests. Remember, all these gradients that are coming in are themselves averaged. They might not have the same number of requests in each one of them, so we do a weighted averaging to end up with one single final global gradient that we can use to update the model. We can then apply that global gradient to the model to update it, and we use a learning rate to control how much impact that gradient update will have on the model. So if we use a very large learning rate, the model will change significantly. If we use a very small learning rate, it will only change slightly. We have to find the right balance to changing the model fast, enough that training doesn't take forever, but not so big that we actually put the model into a bad state. We've also implemented some learning optimizers. So the first one we've built is the Atom optimizer, which is a fairly standard learning optimizer that a lot of people use. So this process I mentioned where we're trying to reduce the errors with these updates is called gradient descent. You're trying to find the minimum, the global minima of the error. But sometimes with the standard stochastic gradient descent algorithm, you can get trapped in a local minima. So you'll be training the model and it'll hit some point and then it won't get any better. And SGD can sometimes get trapped in those local minima. But if you let the model get a little bit worse, it might find the global minima and get to a better overall model. So optimizers like Atom can help you break free of those local minima and end up with an overall better model. It also helps us kind of break free from those things more quickly so we can reduce our training time. So the other component I mentioned was the offline trainer, right? It's the thing that's like the service doing the same kind of model update computation, but it's doing it on historical data. So now I'll describe why we need that. So this is to address that issue that I described about incremental learning where we have catastrophic forgetting. The model tends to forget old things as it's learning new things. And there's different techniques to try to combat that. You can change your loss function in certain ways to reduce the impact. But the technique that we found that works pretty well is what we call memory replay or experience replay. And in this case, what we do is we train on that old data, that cache of old data that we have to produce model updates. And then we can mix them in with the new model updates from the new data in the right ratios, and that does a pretty good job of making sure we don't forget those important things. So we'll typically have about 95% of our updates will be coming from the real-time data, and about 5% come from this offline historical data. So once we've finished updating the model, the final step is to evaluate it. We run a really lightweight evaluation every round of training, so we have a small targeted test set. It won't tell us exactly how the model is doing, but it gives us a directional sense. So we can see if the model is improving. And if it's degrading for too long, then we want to halt the training and roll back to a previous version of the model and start the training again. We may actually let it get worse for a little bit of time, because maybe it's escaping a local minima, but we don't want it to continue to degrade, or we'll want to halt it. And we do this every round because, remember, these rounds are 30 minutes. And so if we kind of were flying blind for too long, we might waste a lot of time on a model that's just getting worse. Every so often, we also want to get a really strong sense of how the model's performing. So every 10, 50 rounds, we'll do a full evaluation on all of our test sets. And that gives us enough information to know whether this model is production ready or not. And we don't do that as often just because it's expensive and slow. So assuming that the model passed evaluation, we then push it back to the service to do the next round of training. And then we just continue this process on and on and on forever, and producing a model at every round that gets checkpointed. And we have that, these evaluation results, so we can get a really good picture of how the model's trending, and then we can pick and choose which ones are prod-worthy that we should release out to our production so it can serve customers. So here's some ASR results. So we ran this system for 9 months, and what we saw was that across the board we got about a 2.7% relative word error rate improvement. And this is pretty decent considering that we didn't roll out a new model architecture or change an algorithm, we just exposed new data to the model. But where it really shines is the 20% relative improvement we saw on new words and phrases. So these are new words or new combinations of words that the model had never seen before, which is very common with trending things and changing usage patterns. So with that, we were able to actually make a significant improvement on those use cases. And then finally, the model degraded by less than 1% on any given test set. So remember this catastrophic forgetting issue, right? We did see that some of our older test sets started to get a little bit worse. And without the memory replay that I described, the degradation was more like 4 or 5%. But with the memory replay, we're able to shrink that down to less than 1% while getting all the other gains. So here's a graph that I'm going to show you that is going to show how the model improvements trend over time. So across the bottom, you'll see months, Jan, Feb, March. Those are the months that we incrementally trained the model. So we started with the model in 2019, at the end of 2019, and we incrementally trained it in January, then February, and March, and so forth. So this purple line is a test set that only contains data from March and no other months. So what you can see is we incrementally trained it in January, and it got a little bit of improvement, less than 1%. And then we trained it in February and March and April, and it continued to improve. But then after that point, it pretty much leveled out, or went down ever so slightly. You see a similar trend if we look at the May data. Again, it improved until it hit about May and then plateaued out. And then finally, the same trend holds in July. It seems like it's getting a little bit better in August and September, but if I extended the graph out, you would see that it would also level out. So what this is showing us is that we're incrementally learning month by month and picking up on some of the changes in usage patterns and trending topics as we do that. And as we get closer and closer to the month of the test set, we finally hit the point where we've learned all the important things we need to learn. And then training on subsequent months doesn't really improve the performance for that particular month. But you can see that the trends are always shifting. So that's why the July line doesn't plateau out until much later, because things are always changing. So we have to continually run this process to keep the model up to date. Here's some examples of things that the system actually fixed. So Alexa, start a Zoom meeting, got corrected to Alexa, start a Zoom meeting. So this is a 2019 model. Zoom was a thing, but it wasn't nearly as popular as it became during the pandemic. And people started interacting with Alexa a lot more to start Zoom meetings. And so by seeing that those requests starting to come in, we were able to fix this error. And then the next two are music examples, where a new artist, Olivia Rodrigo, we were getting her name wrong, and then by using this self-learning system, we were able to correct that. And finally, Xavier Tears was corrected to Savior Tears through the same approach. So along the way, while we were building the system, we had some useful learnings that I wanted to share. So the first one is that we found that large batch sizes are really successful in reducing the training time. So remember, a batch is, every round we don't just update on one single request. We batch up on each host for a period of time. And so that's what I mean by a batch. How many requests do we combine together on one model update, one round? And so in our traditional approaches, or traditional offline approaches, batch sizes can be somewhere around like a few hundred to maybe a few thousand. And that means, but the downside of that is you have to go run for maybe 10,000 rounds. And remember, our rounds take 30 minutes, so that would be essentially forever. So we want to figure out how to shrink that down. So we thought, instead of having many small batches, what if we had fewer large batches? Still train on the same amount of data, just group it differently to reduce the number of rounds. And so that's what we experimented with here. So we started with a 9,000 batch, so a batch of 9,000 requests, all the way up to a batch of 307,000. And if you look at these bar graphs, they show you what the word error rate improvement was on different test sets. You can see that like the green one, the global test set, got a little bit worse with the bigger batch sizes, but not too much. And you can see that the pinkish one, messaging actually did better with the large batch sizes. And the other two stayed pretty much about the same. So that's great. We can use these really large batch sizes and not hurt the model at all. But the real big takeaway is this yellow line. So with a batch size of 9,000, it takes about 1,700 steps to get to this level of improvement. And that's about 35 days. If we look at the 307,000 batch on the far right, that only takes 50 steps, 50 rounds. So that means that we can actually train the model to the same level of improvement in just 2 days. So that's a pretty big win. It makes our approach feasible for quickly getting these improvements out to customers. One thing I should mention as a caveat, remember, we're incrementally training an already trained model. We're applying these deltas on top of this fully trained model. If you try to use a batch size of 307,000 on an uninitialized model from scratch, you're going to get really bad results. So this works well in this technique. You need much smaller batch sizes when you're kind of starting from scratch. So a few more takeaways. One thing we were really concerned about was temporarily ordered data. So remember, we're processing data on the fly in real time as it's coming into our system, which means it's coming in time sequence order. In traditional offline training, you take all your data, you shuffle it around to avoid that, so you get a nice distribution, and things aren't in any kind of biased way. So, again, if we take a small window, a 30-minute window, and it's in the morning, maybe it's people stopping their alarms. And so then we were worried that that would impact the model. But it turned out that we actually didn't see any degradation due to this temporal ordering issue. And in some cases, the results actually got a little bit better. But our takeaway, our insights into why it didn't hurt the model are two. One, we are using these really large batch sizes of 300,000. So it's enough data in there that you get a mix of things, and it's hard for it to be just about one thing. So the updates are not all that biased, even if they're a short window of time. And secondly, because we're just kind of fine-tuning the model and we're applying these updates, no single update has a huge weight on the model. So even if one was biased in some way, it doesn't really greatly impact the model. Another important takeaway was this memory replay to prevent catastrophic forgetting. As I said, we saw some bigger degradations before we added the memory replay, and then that brought that down to a reasonable number. And then the final takeaway was that data selection was the most important aspect of our system. We tried different algorithms, different parameters, we tried different labeling techniques, different teacher models, and they all had an impact. And it's true that better labels give you better results. But the thing that moved the needle the most was the way that we select data. If we are more careful about how we choose the best data for learning, then we end up with the best possible results. So that's an area of focus for us now, how to continue to evolve our data selection and make it smarter and better. So in terms of next steps, one thing we want to do is we want to never stop learning. So we want to just run this system in perpetuity, continually improving models. But we also want to take it a step further. We hope to achieve what they call lifelong learning. So it's learning more like a human does. So you continually acquire new knowledge, which our system sort of does with these 30-minute updates. But then you can also use that new knowledge to fine-tune your existing knowledge. And what that enables you to do is then build up your knowledge base and progressively solve more and more complex tasks, like a human would do. And then the final challenge we have with lifelong learning is we have to be able to transfer knowledge from model to model efficiently. So if we're training a model through this lifelong learning system for a long period of time and it's gaining a bunch of knowledge, and now we have a new model architecture that's better, because the state of the art in ASR is always changing, how do we transfer all the learnings from the model that we currently have to this new model so that we don't forget all that stuff and have to start from zero again? And so once we've achieved those challenges, we can, I guess, claim that we have a lifelong learning system. The other direction we want to go is we want to move to the edge. So we want to take the learnings we've gotten from building this system and some of the components and then shrink them down and move them to devices so that we can do true federated learning. And we envision in the future like a hybrid federated learning system where devices that are capable of running FL on the device will run it there, and their data can stay local. And devices that can't support that will still stream to the cloud, but they'll be intercepted by a real-time service so that we don't have to persist the audio. And then we can combine the learnings from both the federated learning system and the real-time learning system together to continually keep our models up to date. So that's it for my presentation. So today, Angela gave you an overview of Alexa's speech recognition, and then she described why we wanted to build a self-learning system. I then gave you a quick introduction to self-learning techniques and walked you through our system. So now I'm going to open it up to any questions that people may have. Yeah, and if you could use the microphone right there, that'd be...
Hi, I'm interested in the memory replay part of this. I'm wondering, how do you select the images for the memory replay to forget the catastrophic learning? And do you continually update the memory replay images, or not images, the audios as well as as you collect more data?
Yeah, that's a good question. So today we start with a fairly simple approach. We have these data sets prepared, these human labeled data sets prepared, and we just randomly sample them every round. Like I said, 5% of the overall data that we learn from is randomly sampled from that. And we do this every round. So every round we're selecting some other set at random, and that seems sufficient to counteract the catastrophic forgetting. And we do, as new data comes in that does get human labeled today, and in the future will be synthetically generated, we'll continue to kind of expand that pool, maybe trim off the end, but keep doing that same process on newer data too.
So first, let me say, it's an amazing product. I have something like 8 of them in the house, right? It causes some contention. Is there any thought to separating the speaker from the microphone? Can we get a device that doesn't have to compete with itself for me to interrupt it? So if I have 5 in earshot, it often asks me, did I respond from the correct device? Right, so we're playing games with the ones at home that say, I'm going to call you Dot, and I'm going to call you Computer, and I'm going to call you Ziggy, and we're trying to figure out how we can address one.
Yeah.
But we still have that conflict of, if you're on the one that I'm trying to talk to, and I'm saying, hey, wait, you got it wrong, I really have to push sometimes to say, no, stop.
Yeah.
So that's kind of the first question I
Sure.
have a follow.
Yeah, we do have we have a system called ecospatial perception, right? ESP, that its job is to figure out which one you're actually speaking to, and it uses like your proximity and the volume. But I agree, like I often wake up the wrong one too. I don't know. These guys might know better than I do what the what the progress is there to improve that.
Okay.
Maybe we can talk afterwards or something.
Sure. What about you allude to the compute on the edge. How much of it is done today on the edge, like time and timers, time of day, timers, and could we get filters for, they're all basically going to hear the same thing. So my tap when it runs is always going to be my tap, not, is there thoughts to how much compute is going to be on the edge?
Yeah, that's a good question, tough question to answer. So we do have, obviously our wake word engine runs on device because it has to be the thing that wakes up when you say Alexa. And we've actually moved ASR to some devices with our Blue Bottle project. So actually the speech recognition happens on the device on these a handful of device types. There are some of the ones that are, have a little bit more compute, so we can actually do that on device. But there's definitely a push to move more and more things onto device, including federated learning. But it depends on the device type, the available capacity, and we try to keep these things fairly lean to keep the cost low for customers. So there's that balance there, and how do we get more things on it without increasing the cost? But it's definitely the direction we want to go. We want to move more and more compute to the edge.
There are, as you mentioned, certain intents that are done on the edge for a select number of devices, and then earlier this year we also launched a customer setting where you can choose to keep audio from your voice requests on your device. And so again, as Aaron mentions, there's a lot of complexity to scale across the very many different device types that we have, but that there are growing number of features that we have on edge.
Thank you.
Yeah, I was just going to ask that 5% number, how was that determined? Was that determined empirically, or was there some literature behind it?
Our scientists experimented with all kinds of ratios of the real-time updates and the historic updates, and found that 5% was a pretty good number. We wanted to try to make it as small as possible because we didn't want to rely on historical human transcribed data if we could, but it turned out to be really important. 5 was the sweet spot where it was small enough that we were kind of okay with it, and it gave us the improvements we wanted.
Because normally in most systems that I've worked with, it tends to be a higher number than 5, so it's probably just the nature of the data drift and distribution.
Yeah.
Yes, I often use our Alexa for music playback, and I noticed for a long time in the beginning I would have to specify the song and the artist in order to get the particular performance I wanted to hear. But more recently, I can just give it the song title and it consistently remembers who I want to hear singing that track. Is it truly learning my tastes, or is that just my perception?
Yeah, that's a good question. I think, we do personalize based off of historical usage as well. And so I think some of, if it's a song that you request frequently, and we are trying to pick up preferences and at the individual user level. So
I was
that's
wondering-
great to hear.
Yeah, it's working. I was wondering if it's individual or demographic or geographic, but it truly is. That's awesome. A little scary, but awesome. Thank you.
Is it, I might have missed this, but there was, you walked through the example of like Olivia Rodrigo was getting parsed as Olivia Rodriguez.
Yep.
And then with continual training, it can pick up on that's a new trend. But is that, do you have labeled data for that? Is there an annotator saying this is what the correct pronunciation is? Because otherwise, it seems like it would just start to see Olivia Rodriguez more, but that's not
Yeah.
the signal.
So, so for those examples, we didn't add. I mean, we added historical data, human labeled data, but not. It wouldn't have had Olivia Rodrigo in it either. So it was able to correct that error just by using the teacher labels. So the teacher had been updated with like weak signals to or something to correct that error, and then it was able to teach the student the correct thing. Does that make sense?
So that's trained. So there is something trained on a data set that is like aware of the. Is the teacher label trained on text data that it can actually see that like word is the word that is showing up more frequently?
Yeah, we ingest a lot of text data from various sites that we get information from, and then we can feed that into the model.
And as Aaron mentioned, there's a variety of sources, and so we can ingest data, but there's also the weak signals that we get either from implicit or explicit customer feedback. For music specifically, we look at playback, like how long a customer will continue playing the song, and so if they stop playing the song and play another song within a certain amount of time, then we use that as a signal as well. Or as Aaron mentioned earlier, they could simply say, Alexa, you got that wrong, which we use as signals as well.
Gotcha. Thanks.
Any other questions?
All right. Thank you.
Thanks a lot, everyone.